To achieve the kind of seamless, real-time variable speed control over a heavy industrial conveyor system seen here, you need highly precise programming logic. Instead of risking expensive physical hardware during the initial programming phase, we are going to build a fully functional 3D simulation to test our variable frequency drive, or VFD, speed control logic. To follow along with this process, you will need a blank workspace open in Factory I/O and a basic understanding of how to navigate the 3D camera controls. Constructing a perfect virtual environment mapping our physical components is a mandatory first step. Finding and fixing a logic error on a virtual motor is a learning opportunity. Deploying that same error on a real factory floor can destroy machinery. This outlines our S1200 PLC architecture. Single-phase power provides 24-volt output. We map 24-volt lines through start and reset buttons into digital input terminals. We map the potentiometer to the analog input and route the analog output signal to the conveyor's drive and display. This physical wiring map dictates the virtual architecture we must build in Factory I/O. Open a new project in Factory I/O and locate the 4-meter conveyor in the library. Drag it into the empty 3D space and drop it onto the floor grid. A conveyor needs material to transport. Place an emitter object vertically at the start to continuously spawn boxes. To prevent boxes from crashing the simulation, place a remover object at the opposite end to delete them. Establishing these boundaries and continuous material flow creates the environment needed to test our control systems. Now we build the operator workstation. Grab an empty control panel pillar from the operator's menu and position it next to the center of the conveyor belt. This highlights a positioning trap. Dragging buttons often leaves them floating in midair. Holding the V key constrains movement vertically, allowing accurate flush mounting. Using that vertical constraint, mount the green Start button onto the top left of the panel face, followed by the Stop and Reset button directly below it. Next, grab the digital display unit and mount it to the top right of the panel to provide our visual speed reading. Finally, bring over the potentiometer component and mount it just underneath the display screen. This dial acts as our manual speed control input. Precisely aligning this control panel ensures that when we click these buttons later, our simulated operator inputs perfectly mirror a real-world factory workstation. With the hardware placed, we have to configure the internal software settings for the conveyor component. Right-click the conveyor track and open its configuration menu. By default, the conveyor is set to digital mode, which only allows rigid forward or reverse toggling at a fixed speed. We need to switch the setting to analog. Setting the conveyor to analog mode allows the virtual motor to interpret the scaled 0 to 10-volt signal, making smooth, variable speed control possible. Now go to the top menu and open the driver setup window. From the drop-down list of controllers, select the Siemens PLC Sim. This table illustrates our exact channel requirements. First, allocate one analog input for the potentiometer and 2 analog outputs for the motor and display. Next, allocate 2 digital inputs for the buttons and 2 digital outputs to power their internal indicator lights. Assigning these driver channels acts as the absolute bridge. It ensures every button press and dial turn in the simulation will be properly read by the logic we write next. We now have a fully assembled 3D track, an aligned control panel, and a perfectly mapped driver configuration. The physical layout is completely wired and prepared to receive intelligent instructions from a controller. This is the core advantage of simulated environments. We can test complex sequences, like spinning up machinery to varying speeds, and verify our exact logic without any risk to physical equipment. In Part 2 of this series, we will open the Siemens TIA portal, write the ladder logic to control the system, and run the live simulation. Make sure to subscribe to the channel so you don't miss that upload. Building a precise virtual setup takes patience, but it provides the non-negotiable foundation required to write flawless industrial automation code.